Thank you for coming back. And I have to say that unfortunately it's going to be increasingly more technical, but today it's kind of halfway. Tomorrow is going to be probably the one that is a bit more heavy. So here you see that I acknowledge also the ISERM because part of this work was done during the special semester last at ISERM. So I'm going to give a little bit of a summary of the talk to start with so that you can see there is some connection with what I talked about last time. In fact, we recall the global wave pulses for the cubic periodic to the NLS. Then I will remind you what is the transfer of energy. I gave a little bit of an idea last time, and I will go more into details. And if you remember from yesterday, there was something about polynomial bounds in time of the HS norm of these solutions. And I will stress in particular today the difference between the rational and irrational case in terms of the torus or the periods with respect to the first and second coordinates. Then I said we talk about polynomial bounds, but also we talk about the existence of solutions that might have a growth. And I mentioned yesterday two examples, the one with the I-team and the one with Carl and Faux, and then some updates on the irrational case. Okay, so if you were here yesterday, then you remember that the sort of protagonist of the whole talk was the 2D, we are in 2 dimension, cubic, nonlinear Schrödinger equation, which is defocusing. So they have a plus sign here. Why torus? Well, because this just means that we consider periodic solutions. And since today I will talk specifically about the difference between a torus, which is rational or irrational, let me remind you what that stands for in dimension 2 at least. You can have a similar definitions in higher dimensions by taking vectors, but anyway, this is easier to say. So we look at the Laplacian. This is the Laplacian of my torus. And so the symbol, if you like the eigenvalues, is going to be, well, if you are in a square torus, it would be just the modulus of the frequency k. But if you have different periods, then of course this constants here will not be the same. And so you will have the first coordinate square times positive quantity, which depends on the period of the first coordinate, and then same thing for the second coordinate. So the index 2 here is square, the one at the bottom means first, second coordinate. And of course, this other constant here, it's also positive. Okay, so if the ratio between these two is a rational numbers, we call the torus rational, and if it is not, it's irrational. Now, yesterday we went through the Strickart testimates. I went through the fact that in order to define a solution for this initial value problem, we really solved the Duhamel integral equations, and we do that via a fixed point theorem. And we use the Strickart estimates. Then the bottom, what we say that at the end, what you get out of that, it's first a local solution for any initial data in HS for S strictly greater than 0. And then if you are in the defocusing case, like in this case, and you use observation of these two integrals, the mass and the energy, then you upgrade that local wave pulses to a global one by iteration. But you have to make sure that this quantity are well defined. So that's why S is greater or equal than 1. And I mentioned, yes, that you can actually have a global slightly below 1. But for what I'm going to talk next, I will just consider basic smooth solutions. So this is just good. So the summary from one of the parts that I illustrated yesterday is that, and this is due to Bourgain, if U0 is in HS, S is greater or equal than 1, there exists a unique global solution U. This lives in a certain space. We call this the space of Bourgain, which is included into continuous function from time into HS for any time, any interval, as large as you please. Okay, now the question is, what do we know about this solution when we let t goes to plus or minus infinity? Well, this was also mentioned yesterday, if we do not impose boundary conditions, so we are, and here I'm always saying two-dimensional, we are in the whole plane, then we have scattering. What that means is that I can find these profiles, U plus, U minus, in the same space or regularity of order S, such that when I evolve linearly, U plus, if I'm going to plus infinity, U minus, if I'm going to minus infinity, and I subtract the solution of the nonlinear problem, their difference in HS goes to 0. So what that means is that at infinity, both plus and minus approximate a linear solution. Now, any linear solution is uniformly bounded in HS because the ST, the Sobolev, the Schrödinger group, it's unitary. So we get a uniform bound. So this is certainly something that we know in R2, and I mentioned that it's a result of that. Now, in the periodic case, it's very different because we are not allowed for the dispersion to act because we are putting boundaries. And again, this is the concept that I say, yes, that we are interested in understanding, and this is a transfer of energy. It can be viewed on the much larger umbrella of wave turbulence. It's just one fact that is studying wave turbulence. And what that is the following. So I'm going to start at time 0 with the initial data in terms of, I'm looking at this in the frequency space. The initial data is concentrated near a small k, and I want to know whether this bump here is going to move to higher frequency k for large time. This is called transfer of energy or forward cascade. Now, if there is such a movement, just by using the conservation laws, we understand that this is kind of a rigid thing. It's not going to happen that easily. One first realization of that is the following. If you look at the area of the subgraph of this, well, that has to be constant because that's exactly equivalent to the mass, and the mass is constant. So that's one thing that you know. If there is a movement going from low to high, well, the sub area has to be constant. And I'm not even using the energy, which also is constant. So you know that this is not going to happen so easily, and because of that, it's not going to be easy to see it somehow. Now, the solution UTX, this is just like a general remarks in a sense. So the solution UTX will take some time to see the boundary. So if you have a big domain with boundary data, periodic, farther away, of course, it's going to take longer time to see anything like that. But eventually you hit the boundary and that effect will be visible. On the other hand, you can also imagine that if the torus is irrational, if you think about this train of waves hitting the boundary coming back, the irrationality of the torus should give you a little bit more room to spread because you're not going to go back in it after finite hits. So this is just purely speculative at the moment. So let's try to see if there is a way of making this a little bit more concrete in terms of an observation. Okay, so I mentioned yesterday that Bourgain was the first one that taught us that one possible way of understanding whether this quantity is going to migrate to large K is by actually looking at the weight, which is the Sobolev weight. It doesn't matter what S is, as long as it's greater than, you can think of it to be much greater than 1. And then sum everything, which gives us the HS norm. And then look at the limit as t goes to pi infinity, or the asymptotic with respect to time of this HS norm. And I remind you that when S is equal 0, S is equal 1, we have a uniform bound from the conservation laws. Now, we already remarked that in R2, there is no growth. That was the scattering, we already remarked that. And as I mentioned yesterday, if you are in one dimension, there is also no growth because of the integrability of the system tells us that there are infinitely many conserved quantity. There is one for each order of derivative, and you can combine them so that you have a uniform bound. So the first example to look at is really the two-dimensional cubic. And this is what we know so far. This is a different kind of works. and also different kind of methods. So if we concentrate, so here I'm purely concentrating on the Schrödinger two-dimension cubic, but of course you can, as I will mention there later, there is other results in higher dimension for different kind of nonlinearity. But in terms of the equation that I have been using so far, we have a bound. It's important to remark, for what I'm going to say a little bit later, that this polynomial bound depends on the S that you put here. Okay, so far that's what we have. And how is this proved? Well, one way of proving this is an idea again of Bourgain that does the following. Now, when you look at the local closeness and you do the Schiff's estimate applied to the Duhamel terms, what you would see is the following. So imagine I'm checking what happens from n-1 to time n. So just fix the time n-1. And then you want to move to n. So that's one step that you do in the local closeness. So in general, when you do that estimate from the Duhamel, there is the linear part, and that would just be the un here in HS less or equal than 1 times the linear part, but then the nonlinear part adds more stuff. So in general, the estimate that you get to go from n-1 to n is the UNHS is less or equal than a constant here, which is greater than 1 times the previous step. Okay, so 1 is expected only for the linear. That's the unitary of the ST operator. And that is what, if you think about having a constant here, which is greater than 1, and you iterate, then you get exponential growth. But we want to beat that. So what Bourgain proved is that, well, you want to put 1 here. But of course, that's not going to work because that works only for the linear piece. You have to take care of the nonlinear piece. But then you definitely have a constant here, which is greater than 1, but the power is less, it's 1 minus sigma. So this is a much stronger local estimate, meaning local because you go from n-1 to n, it's not a global thing. But then you can prove that if you have such an estimate, then you get this polynomial bound where here you put a sigma, the degree is going to be sigma to the -1. So that's why we get this. So that's the idea. Now, how do you achieve this? Well, there are different ways of doing, and for people who are familiar with this, the high-low method, the upside-down I method, the sum energy type estimates, and so on. And I have to say that in general, for any torus, this is what you get. And these proofs that I put here are really independent from the rationality or rationality of the torus. But of course, we would like to improve this polynomial. Okay, so now if we are in the irrational torus, then the situation is better. The two results that I'm going to mention here are not in dimension 2, which is what I have been used so far, are actually proven in dimension 3, but I'm sure there is an equivalent in dimension 2. And says the following: for the nonlinear Schrödinger, this is now the power of the nonlinearity, and P is in between 3 and 5. So we are exactly outside the example that I'm giving you. So we are in dimension 3 and we have a nonlinearity greater than 3. Then it says that in the generic tori, one has this polynomial bound. And the point here is that if you are in the, the irrationality of the torus allows you to put this extra piece here in the denominator. What that means is that the degree of the polynomial that you use, and by the way, here I didn't put here, but there should be an S. Yeah, sorry about that, it's a typo. Still depends on S. So what this tells you is that the rationality of the torus allows you to put something in the denominator that makes the degree smaller. And then you note here that we missed 5. Well, then consider that particular case. This equation in dimension 3, quintic, is called critical. So whenever you hear critical, that's worse than subcritical, which is this situation up here.
What is generic here?
That's exactly, well. So generic is the ratio or the vectors that gives you the rationality of the torus. satisfies some solution of some Diophantine equation. I have to go back to the paper to see exactly what I mean.
So it's, I mean, but they're not rational Theorem, but
are irrational.
These are,
but not all the irrational.
Okay, so this is some kind of bear, or
some kind of what?
Some kind of bear category, or
I have to go back and check exactly what that is. But it's not all the irrational, but certainly it's irrational. Okay. And this is just to mention that it's the result here, it's weaker than the one up here. You see they have a much larger degree, just because this is a critical problem. So you expect more complicated dynamics. But the point that I want to make is that these two theorems, the irrationality of the torus matter. Okay, now what is the expected? This was a question that was asked yesterday. What is the expected band? That we have these polynomial bounds, but what is expected? We don't know yet, except that we have some pretty sharp information when instead of the nonlinear Schrödinger, we look at the linear with potential. Okay, so let me mention these two theorems or these two statements of Bourgain, but I wanted to say that after these statements came out, a bunch of people worked on this problem, more different potentials, different dimensions, and so there is more than that. But basically, this is what tells you a lot of information. So the result says, again, I'm going to take the linear but with a potential now in the torus, but the torus here is rational. Okay, so this results of Bourgain dimension is for the rational torus, and then here you also have some results for irrational. So if VTX is bounded, periodic, also in time, and smooth, then the bound should be no more than an epsilon, t to the epsilon. And then if VTX is bounded, real analytic, quasi-periodic in time, and dimension 1 and 2, and small in dimension 2, then actually it's a log power. So this is linear, with a potential, but we still expect, at least people expect, that the growth should not be very big if it is there. Log probably. Now, what about bounds from below? So what do I mean with this? So with this, I mean, do we actually have solutions that grow, have the HS norm that grow? When Bourgain proved this result here, actually gave us an example of a solution for this linear problem that grow exactly at this rate. So in this context, and then this has been generalized somehow, but what I want to say is that there are sharp results in the linear with potential. So yes, in that case, they are sharp, but in the nonlinear problem, the situation is not clear, and it's not at all, we don't have any sharp results in some sense, neither in terms of upper bounds or in terms of constructions of solutions. Okay, now proving some growth in the nonlinear case. So I mentioned it yesterday, and we'll say a lot more today. So this is some time ago work that they did with Colliander, Kiel, Takok, and Tao. And we started with the same problem that you are now familiar with, and the torus is rational. In our case, it's a rational torus. In fact, it's a square torus. And what it says is that if we fix a certain order of derivatives, so pick your favorite regularity, and pick a small quantity and a large quantity, then we can construct an initial data, which has the regularity we assume we wanted to get, which is small in that norm at time 0. So the initial data is small at time 0. But if we wait long enough, then the solution becomes big in that norm, so bigger than K. So in a sense, I call this a weak result, since we do not know, first of all, what happens after capital T. So we don't expect that things start getting smaller again, but this theorem doesn't tell you anything. Also, in our theorem, we don't have, we know that T is very large, but we don't really have a precise estimate for that. But then later on, people who work in dynamical system went back to it, and they estimate that much better. Another thing that I want to remark is much later, in fact, this is probably a year or so ago, the work of Giuliani and Guardia that says that you can actually get similar results, same result actually, not only for rational tori, but for tori which are irrational, but the irrationality of the torus is very close to being irrational. So in other words, the irrational number is close to a fraction. So in a sense, you can perturb this a little bit in some way. All right, so there is a little bit of a, I want to give you a little bit of an idea how we prove this. Since we are constructing a solution that grows, we have a little bit of freedom in understanding how we wanted that solution to look at. And so I'm looking for a solution U, which is written as the sum of this coefficient times this. You recognize this is what the linear Schrödinger does. Basically, if I were looking at a linear solution, what I will get is exactly this, where this quantity is independent of time and it's just the Fourier coefficient of the initial data. But I'm looking at the non-linear solution, so this is going to depend the way it evolves. So now you plug this U inside your equation, and then you get an infinite dimension ODE system for the AN here. And the way the system looks is like that. Then you can do a little gauge transformation to remove this part, for example. And then what you start thinking is, well, if I wanted something to grow, I expect that growth to come from the resonance. So instead of summing all over the frequency here, so you will be summing over just this restriction, which comes from the fact that you're looking at the Fourier side, you have a cubic nonlinearity, take Fourier transform, you have convolution, that's the restriction. But that's not the only restriction I'm going to put there. I'm going to put the restriction that I'm looking at the frequencies which are in resonance with the outgoing wave. Okay. So you believe that this is what should make growth happening if the growth is there. And that's what you start with. I call this FNLS for Fourier nonlinear Schrödinger. Unfortunately, this is still an infinite dimension system, and there are no tools that are good enough to give you a good dynamics. So then we do something more. In the set of all the resonance frequency, we construct actually a set that's in a sense is finite. And when we restrict on that, we get much easier problem. This is the toy model that we use that has this shape. So now this is finite dimension. J goes from 1 to n, is nearest neighborhood interaction. There is a boundary conditions here. So this is much more manageable. Of course, you might ask, well, you did a lot of reductions. So how do you know that this system here is anything close to what you started with? In particular, even if you can prove some kind of growth here, how do you know that the original one has it? Fortunately, there is an important lemma, stability lemma, that we show that proves that if we do have any growth here, then the original one grows. And this stability lemma is, I wanted to mention because it's going to come up later in a different context as well. Okay, so now we look at this, and the first thing you want to check is whether all the conservation laws are still satisfied. So there is some momentum conservation, energy, mass, and all of that. In particular, the conservation of the mass tells you that the dynamics of this finite dimensional system is going to live on this complex sphere, right? So this is exactly, so if you think about this, this is nothing else than the sum of this. So X stands for these B's. These B's are complex. So the B1, B2, all the way to Bn is a complex n-dimensional vectors. And if you sum the B squares, then that's an L2 norm. And I'm normalizing and I'm claiming that that's size 1. So that's why you can claim that this whole, after normalization, this whole dynamics lives on a sphere, which I represent here. And then you also realize that when you start with a point on this sphere and you start the dynamics via this reduced toy model here, they're going to be like invariant big radii, if you like. So in other words, if, for example, I start on this blue circle, I'm just going to keep rotating here. I don't move at all. On the other hand, what we want to prove is that we have a way of ordering these big circles. And what we want to prove, so what makes things grow, is starting near the first of this big circle, avoiding all the other ones, and ending up to the end. This is, in fact, forward cascade, in other words. So if you manage to do that, then you prove that there is a growth. You go back via the stability lemma and you prove your theorem. So everything is reduced to really a dynamical system question, which tells you that you can actually indeed start from one of these big invariant circle here and sort of avoid the big obstacles ending up at the end. And we do that. And I'm summarizing the whole paper in this picture, but that's really what the proof is. Now, there is another result on this growth of the, it's not really the growth of the Sobolev norms. This is really telling you that if you start with an initial data, which is in this small box, later on at any k, you will find something left over. So this is not about growth of the HS norm, but it's connected. So Carl and Favou proves the following. So we consider the NLS that I have been looking at so far, again in the rational case. We fix again the order on linearity, but in this case, the initial data again lives in a box of radius 2 if you want, but it's also small in the norm HS. And then what they prove is that you, for any k, large k, if you wait certain time, call it tk, you still have something left over at that frequency. So you are bigger than absolute 1 plus sigma. Okay, that's what I show. Now, I want to mention other important results. So this is a result by Hani Pusader, let's see, Setko-Vivishvili. And it says, now the difference with respect to what I have been talking so far is that the problem is not completely periodic. In fact, in one direction, you're allowed to move freely on the line without boundaries. So there is a little bit of dispersion in that direction. And the other tori are rational. And it's dimension 2 and 3. And what they prove is, in fact, their case, that you do have a growth which is of this type. So I was looking at their theorem, but it's not purely periodic as we have been looking at. Another result interesting is by Gerard and Grelier, but which is much more refined than what I have been presenting so far, but it's for the Zegel system. And it's a beautiful analysis. They have a paper on that. Okay, now what can we say for the irrational case? So far, the constructions of those solutions that grow at least a little bit were both for the rational case, or the extension of Guardia and Giuliani, which say, well, you need to be close to a rational. So there is some work which I did with my postdoc, Bobby Wilson, and we consider the rational case. We fix again the regularity. We fix a constant m. We assume that the initial data is smooth but supported the m. Then there is an epsilon such that if you take initial data which are smaller than that, you have this unique solution which is okay in the time that you expect to be. But what the important part is tells you that the size of the initial data stays always smaller than epsilon cubed. So this, if you remember, this is not the same. It's actually opposite of what Carl and Favou tells you, which tells you that you always have something bigger than epsilon 1 minus sigma. Think of sigma just strictly greater than 0. Okay, so what this really tells you is that comparing to the result of Carl and Favou, the dynamics that they have is not going to happen here. Now, this is not telling you that you might not have growth, but you have to wait longer, and it's not happening for the reasons or the dynamics that Carl and Favou used. Okay. Now, this theorem is for small data.
Go back to that slide again. There's something that's a little peculiar. You're getting it smaller. Is that correct? I mean, you have epsilon and you go epsilon cubed.
Oh, yeah. But here, sorry, I didn't mention, outside the ball.
Oh.
So you see there is 0 at the beginning outside the ball. Sorry, I should have, thank you for mentioning that. But it's outside the ball, it's, yeah. Okay, so this theorem is for small data, and it doesn't not say that the growth cannot happen, but just doesn't say it cannot happen with the way Carl did it. In a sense, this is also in agreement with these polynomial bounds that we have seen that are better if you are in the irrational torus. Now, I want to spend just one slide telling you how we prove that result. So the result is proved in the following way. You start with your system, the periodic system. You look at it in the Fourier side, so as a not in the physical space, but the Fourier space, and you activate some Birkhoff normal form reduction. So what does this means is that you're gonna take the whole problem and you separate into a resonant part and a non-resonant part. So we analyze the dynamics of the reduced system, which is the part which is resonant. I'm gonna go back to this resonant or resonant later on and a little bit more specific, but here I just summarize a little bit. And we prove that for this system, the solution is completely concentrated. So we start in a ball of size n. If we just use the resonant part, it's going to stay in a ball of size 2n and nothing else outside. There's nothing else. Now, where do we lose the epsilon? We say that outside the ball, we are size epsilon. It's because you have to go back with your change of variables of the Birkhoff normal form and you lose something. So that's where it comes from.
The resonant part stays in that time. It's within that time, short time frame.
That's right. In that, with that time, epsilon minus 2 that I'm talking about. Yeah. Okay, so I wanted to make a remark because this is really the important fact here. So let's think for a second about this is the, if you like, the symbol of the Laplacian eigenvalue lambda k. The lambda k I wrote it before. So there are this omega 1k, omega 2k. Now, to make things simple, imagine that this is 1 and this is square root of 2, all right? So when you write this resonant relation here, what you see is that there is a complete split between the first coordinate and the second coordinate. So in other words, the resonance set splits into 2 resonance sets of dimension 1, okay? This is why is this interesting? Well, it's interesting because you know, for example, in dimension 1, there is integrability, and so all the HS norm are bounded. So it's kind of like it's not that we can say that the irrational 2D NLS nonlinear it's integrable, but it has certain features of something which is integral. So we are splitting completely. There is no mixing between the first and second coordinates, if you like. Okay, so in other words, what does this really tells us more visually? So first, let's remark that if you have 4 frequencies resonant with each other, they're in 2 dimension, they happen to be the vertices of rectangles. You can show that. In the rational case, the type of rectangles that you have are the one parallel to the axis, you have the diamonds, and then you have these guys, which are degenerate rectangles. Now, both in the work of, and I'll give you a picture in a second, in the work of the I-team and Carl and Faou, it's fundamental that this rectangle is there when you look at the dynamics of the system. And if you are in the irrational case, this diamond shape is not there anymore. It's not part of the resonance frequency. So if you look at, let's concentrate on this result here. So the growth of the theorem that tells that you can start small and become as large as you want in a long time. If you look at the special set that I say we construct within the set of the resonance, the frequency, the set looks like this. You start with the 4 dots, the blue one, forget the blacks, that's kind of like a byproduct of, don't worry about the black ones, just look at the blue. That's where we start, which is the same starting point of Carl and Faou. Then as we expand, we activated this red ones. That's the diamond shape. And then in the next step, we activate these green ones. And then there is a diamond shape up here, and then you keep going. So this diamonds shaped here are actually important for the dynamics. And if they're not there, you cannot move. Okay. Now, that was the result with Bobby for small data, and we wanted to do something for large data. And we start collaborating with Alex Hartby and Yulin Pan. These two people are actually, they do numerical analysis, and they helped us in doing some kind of simulation, and I will give you some pictures at the end of their simulations. So let's consider, just to make things simple, that our irrationality is alpha, and it's just think of square root of 2. That's really what I want you to think about. And what we prove is the following. So assume that S is the order of the derivatives, think of bigger or equal than 3. And U is a solution of, again, the cubic NLS equation, defocusing, I didn't write here, but defocusing, on this torus, with initial data of that regularity and supported in a ball of radius r. Then what we prove is that the HS norm, it doesn't grow more than linear. So you see there is no more dependence on S here. So this is much stronger than what you can obtain if you don't make any restrictions on the torus itself. So that's this is the closest that we got to what we expect, which is the log. Okay, that's the theorem. Now, originally we thought that we would go again through a Bourgain normal form. And in fact, we did that originally. But the problem is that it was, because we are dealing with large data, going back, inverting this change of variable that we make via the normal form reduction, we were just losing control of the error because the data were too big. So that really didn't work. So we changed strategy. So I'm gonna write for you what I mean with quasi-resonant, okay? So we consider not just the set of resonant, but also the quasi-resonant, I'll tell you in a second what it is, associated with the original NLS. We concentrate only on the system which is quasi-resonant. And one thing that was surprising already from the beginning is that actually this is globally well posed in L2. And I'm going to mention the remark later, but I can announce already here. If you remember yesterday, I said that the whole NLS with full nonlinearity, it's still not known whether it's a well posed in L2. Like if I tell you, I give you an initial data which is finite mass, can you tell me there is a solution? That's not known. But for this reduced system, you take the whole NLS, but you just keep the frequencies which are quasi-resonant, which are definition I'll give in a second, then that is well posed in L2. And then we use a stability lemma, sort of like the one that I mentioned in the result with the I-team, to go from this quasi-resonant system to the whole system. Now, it's time to define what is quasi-resonant. And this is quasi-resonant. So if here I had 0, that would be just the resonance set. But what I'm asking is that it's less or equal to this quantity. Now, this lambda, think of it as a large quantity. And this large quantity, as I will show you in a few slides, is what at some point is going to make something small when we're going to start encountering small denominators. So it's you flip it over. A small denominator means that you're going to start seeing this quantity on the denominator. But if you think about this and you are away from the quasi-resonant, then the lambda will be in the denominator, will help you. So I will see in a second. Okay. So as I said in the footnote here, so the constant lambda is used when we encounter the small denominator in the proof for the stability lemma. So the theorem, I wrote this as a theorem exactly because what I said before. So now we are looking at the NLS, but instead of taking the whole nonlinearity, we look at the quasi-resonant part. So there's going to be resonance plus something more. And we assume that the support of the initial data is in a ball. And we first prove that L2 is conserved also in this case. The proof for the conservation of the L2 norm here has to be done not in the physical space, but taking integration by parts, but in the Fourier space, where you have a bunch of symmetrization and cancellation. So that's important. And we prove that it's globally well posed in L2. And moreover, if we start in a ball of radius r, and we are able to define sort of what we call it a boundary, so that there is no dynamics outside that. So if you start in a ball of radius r, if you take a large enough ball of radius m, you have nothing outside it, that dynamics. Okay, here, of course, the m that I'm mentioning will depend on the lambda and the tau and the definition of the quasi-resonant, and of course on the r that starts with. Okay, this is the remarks that I said before. The toy model that I introduced before from the I-team proof, it's sort of a subset of this because it was only the resonant part, while here we included the quasi-resonant. And we proved, as I said in the previous theorem, that we're not going to see anything outside a very large ball. But here, in the rational case, we were going outside. By the way, I wanted to say that if you remember, in the assumption that I made here is that my torus has a square root of 2 for irrationality. And that's not the one that Giuliani and Guardia proved the theorem for, right? So there is this distinction between, this is very rational, and Giuliani Guardia was almost rational. So it's sort of this dichotomy. But how much, we don't know yet, how much irrational. So we have kind of two extreme sides. And again, like I said before, know that for the global well-posed in L2, for the full periodic, NLS is a major open problem because we have a loss of the epsilon in the Strickard estimate. So the corollary that comes from this, by the way, here I say, just step back one second. So here I say global post in L2, but actually there is a preservation of regularity. So if you start with initial data in HS for S strictly greater than 2, the same thing holds. And since the time only depends on L2, you have a global in HS. Okay. Okay, so now we'll start again initial data, which has a support on the ball. If V is a solution of this quasi-resonant, then you have actually uniform bound for the HS norm of these guys. Okay, so it doesn't really grow. But again, you have to, I'm not claiming that there is a uniform bound for any initial data in HS. It has to be compact support. And it's for the just reduced one, not the whole thing. Okay, so the proof of this is, well, it's based on this fact that you have nothing outside a certain ball. Sorry. Okay, so that's not important, the proof, but so I want to show what is that, where does it come, the main point here. So let's, it comes from Roth's theorem. I'm not a number theorist at all, so this is my collaborators that know much more than me. But the main point is the following. So if we look at this whole set and we remove the really resonant ones, then the other frequencies, which are quasi-resonant, not the resonant, you see, I'm just taking strictly greater than 0, but less than this quantity, then these frequencies, the number of these frequencies is bounded. So in other words, they are confined inside a large enough ball. Of course, there are resonant frequency outside a large ball, those you can go anywhere, but the ones that really satisfy less or equal than, strictly bigger than, it's a finite number. And that finite number depends, of course, on what you pick as lambda and tau and alpha and all that. And the next ingredient is that this what I already mentioned.
What Roth theorem are you using? Roth usually means specific numbers like √2 or some
Yes.
great number.
Yes,
That's the Roth theorem.
yes.
So
Now we're looking at √2 in this case.
then it's quite easy for that number. I don't think you would be using the full force of Roth. And anyway, physically, why don't you take a generic
You
number
can. I'm making.
and you don't need to use anything as fancy.
Yes, it's the only thing I want to claim is that when you are strictly above zero, this number is fine.
Yeah.
That's now, yeah. And it's not just square root 2. And then, of course, the separation, the thing that I mentioned before, that when you have the whole set of resonant frequency, you can split into two one-dimensional one. And this is the main proposition, actually. The main proposition says the following. So think of Zk to be the solution of the quasi-resonant set. Now, let's define. This is, if you think about this, is exactly the HS norm. I just wrote by splitting the first coordinate and the second coordinate. Usually you see the absolute value of the frequency to the S, but here I want to split between the two. And I'm also thinking that I'm outside the large ball where there are only resonant frequencies and not quasi-resonant, right? So I'm outside that. And then if you check how the change of this, let's call it partial norm if you want, how that works, so the ddt of that is going to be 0. So there is no change outside this large ball. And of course, this n depends on the delta and so on. So the proof for this proposition is, well, you really write it down directly, and then you just separate the first coordinate from the second coordinates. The resonance thing split completely, and you have a lot of cancellation. So it's actually, you write it down and you see that. There's really no, it's writing it down. But of course, this tells you that there is no, at least for this partial NLS, not the whole thing, but just this quasi-resonant set, you have this nice behavior outside a large enough ball where only the resonant frequencies are left. Okay, now I wanted to just put one slide up to show why this lambda helps, okay? So this lambda helps for the following. So if you wanted to go back to the original full nonlinear Schrödinger, you have to examine what happens to the non-homogeneous term that has frequencies in the complement of the quasi-resonant set. So that's what you have to control, right? Because you want to make that small. Well, the point is that when you write it down, and this theta here is exactly the resonant part. So if you are completely resonant, this is going to be 0, it's going to grow. There is no way. But if I am in the complement of that, just by doing integration by parts, you can see that you will get this quantity in the multiply. And so, okay, here you're going to lose a little bit of derivatives. And then you say, what do you do with that? Well, we have already the polynomial bounds from previous theorems, right? So you can use that fact already to control the fact that you lost some derivative. But what you gain is the 1 over lambda, and 1 over lambda can be made small by taking lambda large. So that's really why this whole thing works. Okay, now I wanted to show this visually.
In your problems, do you always have your resonance are involving 4 things?
Yes.
Because that's,
yes.
You had 3.
Yes.
You would have to use some serious numbers.
Okay, that's no, this comes from the fact that we are looking at the cubic NLS. Yeah, but that's interesting because in fact, we are realizing in different contexts that if you have a bilinear nonlinearity, it's much more like for the KDD perhaps, it's much more complicated.
But these kind of expressions are integer linear, a quadratic form,
Yes.
lambda in irrational angles.
Yes.
And if it's signature 2,2,
Yes.
a little easier than signature 2,1. This is Oppenheim.
Okay, so
So it's kind of, it'd be interesting if you needed to deal with a real hard case done by Ratner.
But you see, one thing that I found, and I don't know, like this that I'm showing to you, it's really an example of a very rational thing. And then, well,
Very irrational.
yes.
Yeah.
So, and then the paper that the other people did, which were able to extend our calculation for the rational thing by for certain irrational tori that close to be rational. But where is the what happens in between, and where is the you know, there is no. Okay, so this is just a little bit of a numerical experimentation that my collaborators did. So let's see what this represents. So this is the levels delta tau quasi-resonant set. I can't remember what delta is and what tau is, but yeah, tau is here. It's 0.1, but I don't remember what delta is. So we start with this a little. This is at the beginning at time 0. And then which frequency gets us excited as we move forward. And the interesting thing is that, well, let's see, here it's alpha equals square root 2. That's the irrationality of my torus. So not much happened a little bit that this guy gets expanded. But for alpha equals 1, the square torus, if you want, it's quite bigger and quite larger, as you can see here, a lot more that's excited. And this is a picture of the boundary. Somehow this is think about the yellow square to be where the initial data lives in a small 1 by 1, if you like, square. And then after, okay, this is the time that we measure at both of these situations. This is in the rational case, and this one is in the irrational case. So it gets much larger. And this is just some the growth of the Sobolev norm. Again, in the case in which we are, this is the square, and this is, of course, this is for certain initial data. It's not obviously all the initial data. And this is just the dependence of the size of the initial data, how it grows. So this is a smaller initial data, very little growth. So it depends. This is just to say that how much it grows also depends how you start at the beginning. And I think that's it. So thank you very much.
Are there any other questions?
Well, I would just like to understand in this theorem that you were proving about the fact you've got bounds without any S dependence or somehow
Yes.
uniform growth.
Yeah.
So what was the mechanism for that? I didn't.
Yes, so the mechanism is the following. So a little summary. So we take the original equation and we split into the quasi-resonant and the remaining.
Yes.
In the quasi-resonant, really why I could just split the resonant or resonant, but the point is I need this quasi because I need this lambda to be large when I do the next part, which is my stability theorem that tells me that quasi-resonant dynamics is closer to the original one because the rest is small. And to prove that the rest is small, I need this lambda. Then once I concentrate on the quasi-resonant, just think about just the resonant at that point, because the frequency which are quasi-resonant, they're all inside a box. And what happens outside is really only resonant. Now let's concentrate on the resonant. And what I'm saying is that the resonant frequencies, they split into two one-dimensional resonances. And when you start looking at how the HS norm changes for this in time, you can use this splitting almost like getting back to a 1D NLS. And in there, you prove, because of the splitting of the frequency, you can prove that basically outside, there is no much change. There's no change. So that's the summary of the theorem.
Do you use the integrability of the 1D case at all?
Not directly, but what it's used is that there is a really nice, if you do the calculation in the 1D for the DS outside, there are nice cancellations that happen, but only in one dimension. I mean, but since we can split this in one dimension, that's what is used. And not directly, but that's sort of a, yeah.
So if I go to NLS in one dimension, and I break integrability, for example, by adding a linear term, right?
Right.
So then can you get very good bounds? I mean, it's not obvious that you're bounded anymore, the HS norm.
Exactly, it depends how whatever you add behaves. You
So
know,
I just add a linear term, I want to know how the HS.
like
norm-
linear term in like potential.
No, just add a 5. Instead of 5 cubed, you add 5 cubed plus 5.
Okay. Mhm.
Just that, no potential, just, but I think that already breaks integrability.
Yes.
So then do you know how? Presumably, there's no uniform bound anymore. You don't have integrability,
Yes.
but do you know anything about the growth of the HS norms in that case?
No, I have to think about that.
That should be much better.
Yes, much
But
better.
you're integrable,
Yeah,
maybe you can get log there.
probably.
So this is very specific to the cubic, though.
Yes, yes, yes. Even if you do quintic in 2D, that's no longer, it's not that cancellation that I mentioned, it's not happening. Right, so it's even in 1D quintic, that's it's not gonna happen. Very specific to the cubic.
So I didn't quite catch where you needed the rational torus in your norm growth example in the first theorem.
Where we need the rational torus. Okay, so in the construction of that set, you are in the resonance frequency and then you construct a set there.
Sphere.
No, it's before that. So before you go to the toy model, right? So you're making a bunch of reductions. You first are in the resonance set that's very big, and then within that, what you pick is the one they set here that. Let me see if I can go there. Pictures. This one. Yes. So this the dynamics of your of the thing that grows starts with the blue and then moves this diamond here, and then it moves another rectangle and another diamond. So this configuration here, it does not happen if you are not in the rational.
And that is needed to move to the toy model. Okay, I see. So it has nothing to do with the toy model itself, with the geodesic flow on sphere.
That's right. You can make the toy model also for the irrational thing, but it will not have the dynamics that you want.
Yes.
Are there any invariant measures now for this flow?
For the cubic NLS rational, irrational something, yes, the Gibbs measure is the invariant measure.
So you got a logarithm in the invariant measure, right? So that may also be a signal that you have a.
I never
Yeah,
connected
order
these
and-
two things. Yeah, I never connect these two actually. But yes, we do have that invariant measure.
Okay, if there aren't any more questions, thank you again.
Thank you.